Hello, welcome again. That's what the last lecture what we have. See, we had a discussion about high frequency response. Actually, we supposed to start with this high frequency response in last lecture, is it? And I told you that at higher frequencies we have a separate module, that is pi module. At lower frequencies we have H module that already we have studied in fourth chapter, the previous one. Now, this modules are really important. The transistor is analyzed at lower frequencies with the help of hybrid model, that is H model. Now at higher frequencies the transistor's frequency response or transistor is analyzed using pi model. So that's why now it is very much important for us to understand this pi model first, is it? Because by using that pi model we are going to analyze a transistor at higher frequencies. So analysis of a transistor at higher frequencies, it means that's what high frequency response analysis or high frequency analysis of a transistor. Right? We are going to have a frequency response curve. There is a small change in the shape at higher frequencies. That thing is known. Right? So start with higher frequency analysis. The knowledge of pi model is really important. So let us start with this pi model first. Let me write it as high frequency pi module. High frequency pi module. That's what the title. It's not happening. Now it is okay. High. Yes, it is working nicely. Let me check whether I can type somewhere. Insert text. So pi module for transistor. The most important thing is that we are in the amplifier world. We are in the world of amplifier. That's what we are taking frequency response of an amplifier. At lower frequencies gain decreases. Who is responsible? That we studied. At higher frequencies gain decreases. Why and who is responsible is that part of concern now. But to think about the gain decreasing at higher frequencies and who is responsible for that, why it is decreasing, we must have a knowledge of pi module of a transistor. That's why we have started with this pi module. As if now pi module of a transistor, let me tell you that transistor alone cannot work as an amplifier, is it? That transistor, or what I can say a BJT alone can't be an amplifier. What I need to do it, a transistor plus biasing, then it will work as an amplifier. Yes, transistor को bias करना पड़ता है, then it will work as an amplifier. So what I'm doing, that biasing means what? I'm connecting some external resistors and capacitors, especially resistors only. So what I'm doing in biasing, I'm connecting extra resistors to the transistor. Is it? Those are what? Lumped components. Is it? Lumped components means that component that we have connected in the circuit, we have connected to the transistor. Is it? So those lumped components are there with the transistor in amplifier circuit. We have connected it. Is that? So apart from that lumped components, we have some distributed components also. So what are those distributed components? So that distributed component means some internal resistance and capacitance of a transistor. Look at this, internal resistance and internal capacitance of transistors. Those are distributed components, is it? And those distributed components will never come in picture at lower frequencies. They stay quiet, they remain silent at lower frequencies, because at lower frequencies they have no effect on them, is it? उन पे कोई फर्क नहीं पड़ता whether the frequency, if the frequency is very less, is it? they remain same. They remain in a rest state. They become silent at lower frequencies. But as you go on increasing the frequency, then those components, those distributed components, those internal resistance and capacitance of a transistor, they will come up. Is it? So it means at higher frequencies, and that's why I told you at higher frequencies, internal capacitance of a transistor come in picture, and now they are responsible to decrease the gain of amplifier. That's what the conclusion we have drawn at the first lecture, is it? Gain decreases at lower frequencies. Look at this, at lower frequencies, who is responsible? Bypass capacitor, coupling capacitor. At higher frequencies also gain decreases. Who is responsible? Stray capacitance and internal capacitance of a transistor. Is it? So those internal capacitance, they will come up only at the higher frequencies. Is it? That's why. Now again, it's not only capacitor who come at higher frequencies. Some resistors are also there in the transistors. So those resistors, those internal resistance are also there inside the transistor who come in picture at higher frequencies. Is it? So what are those? Some capacitors and some resistors. Is it? So now they come up only at higher frequencies. At lower frequencies, they remain silent because they have no effect of lower frequencies on them. So that's why they never come in picture at lower frequencies. But as you go on increasing the frequency, they show some effect. Is it? They come in picture and they started reducing gain at the higher frequencies. As if now they started reducing gain at higher frequencies, it means now we found two things, that C and R, that is internal capacitance and internal resistors, are responsible to decrease the gain at higher frequencies. Is it? Now as if I concluded that those are there at the higher frequencies, now where are those actually? Is it? Where are those? So to understand them or to locate them inside the transistor, let me draw the transistor structure. Is it? So let me draw the transistor, emitter, base and the collector. Let me draw it here. Okay, I'll draw it with the help of this thing, one line. Let me take another one also. Yes, that much is okay. Again, let me join them. Let me join this part also. Okay, upper part we'll treat it as a collector. So that much collector is okay, yes. And then base, that much base is okay. That much base is sufficient. And now let me mark the emitter also, that much emitter. So now emitter, base and collector are ready now. Look at this, let me join them. Okay, let me call this as collector terminal. Let me call this as base terminal. Is it? And that one terminal that I am taking from the emitter, this is emitter lead or emitter terminal. Is it? Now see, there is a resistance. Look at this, let me draw a symbol. Now look at this, a transistor symbol I have drawn. Emitter, base, collector, three terminals I have shown. This is one collector, this is emitter and this is base. Now there is a resistor present between base to emitter. There is a resistor present between base to collector. There is a resistor present between collector to emitter. So three terminals are there. So in between these three terminals, resistances are there. Is it? Now this thing. So 1, 2, 3. Three internal resistances are there. Now apart from three resistors, is there any capacitances? Yes, obviously, because it is a junction. Let me draw a junction. One, this is a junction. So when base and the collector meets, where it is a junction. What you call this junction? As base to collector junction. Like this, we have this also. This junction is what? Base to emitter junction. So as if junction is there, there must be a junction capacitance. Is it? There must be a junction capacitance. Now this junction, let me call it a junction J1 and junction J2. Is it? So junction, we forgot J1. This is J1 and this is J2. Now as junction is there, junction capacitance must be there. Is it? So the junction capacitance between base to collector, let me give it name as capacitor, that is CT, transition capacitance. Is it? And this capacitance I will call it as diffusion capacitance. Is it? I'm just giving some name. Now why I'm giving some name, and we'll come towards it after we finish with the resistors. So let us start with first resistor, then come towards the capacitor. Just assign them. Two capacitors are there inside the transistor, and let's check three resistors. Where are those? Now somewhere I need to measure a resistor between base to collector. Do I need to show the resistor like this between the base to collector? No, it doesn't make any sense. Why? Because it is the outer resistance, then the resistance present between the base terminal and the collector terminal. So those are terminals. Na? This is base terminal, this is collector terminal. So it may a resistance present between base terminal and collector terminal. So that doesn't make any sense. So that's why considering the resistance between the terminal is not needed. What I need is an internal part resistance. Is it? So that's why I need to select one reference point. Is it? So हमें अगर resistance measure करना है तो किस point से measure करना है? Some reference point should be there. So that reference point I will mark somewhere here at the center. That reference point inside the base. So as if my reference point inside the base, I will call it as B dash, because this is actual B, that is base. So I will call it as virtual base. Look at this. So what is that B dash? B dash is virtual base point. This is virtual base point, or what I can say, it is a reference. For me it is a reference. So now there is a small resistance present between a collector and the virtual base. Look at this. Let me draw a small resistance. This. Now as if now I am saying that from base to collector there is a resistance, internal resistance. Is it? So what is that actually? Let me give it a name as small r, that is resistance present between virtual base, that is B dash, to the collector. So now it is R B dash C. Agreed? The same way I can draw an internal resistance present between virtual base and the emitter. Now notation will be small r, then with reference to virtual base. Now it is to the emitter, not to the collector, it is now emitter. Look at this. That is R B dash C, R B dash E. Now look at this. From this virtual base to the actual base terminal, there is a small resistor. Now what should be the name of that resistor? Obviously the notation will remain same, it is small r. Now I can write it is B dash B. Look at this, virtual base to actual base. Yes, that's how I can show three resistors, that is virtual base to collector, virtual base to emitter, and virtual base to actual base. That resistor, that is virtual base, let me write here, that is R B dash B. This is called base spreading resistors. Base spreading resistor. So why it is called base spreading resistor, that I'll explain in few minutes only, why it is called base spreading resistor. For the time being, I'm just giving a name to that, base spreading resistor. Base is actually spread out. Right. So how it is spread out, in what condition base gets spread, I'll explain it. It's an extra thing. Now three resistors that I have shown, is it? So am I missing any resistor? Look at this, base to collector, base to emitter, base to base, three resistors are there. See, collector to emitter, this resistor we have covered. Base to collector, yes, it is done. Base to emitter, yes, we have covered. But this collector to emitter resistor we have not covered here. Now where to show this? Is it? That is this point. Look at this. From collector to emitter. Do I need to draw a complete line from collector to emitter like this somewhere? No, it's not possible. So it is present, but I can't show it in the structure because of my reference point. Is it? So that's why one resistor is there that cannot be shown here. What is that resistor? It is R C, that is collector to emitter, RCE. Is it? RCE, collector to emitter, or you can clearly say it can be a REC. No, it's not good to say RCE, REC. So it is always referred as RCE. Now just check how many resistors we have. Let me make a list. The first resistor is R B dash C, second one is R B dash E, then R B dash B, then R C E. 1, 2, 3, 4. 4 resistors are there. Is that? Now how many capacitors are there? Okay, now come towards the capacitor. Is it? So when transistor is used in amplifier, basically it goes into active region. So when it is in active region, one thing is known, that junction J2 is a reverse bias, junction J1 is a forward bias. So the junction which is in forward bias, is it? The junction which is in forward bias shows a capacitance, that is diffusion capacitance. Is it? That is diffusion capacitance. Okay, let me write the name as diffusion. Diffusion capacitance. And the junction which is in reverse bias shows a transition capacitance. I will write a name here. It is a transition capacitance. Was that? Now as we have referred resistors with respect to the base, obviously the capacitors also has to be represented with reference to the virtual base. Is it? If I want to represent it in a virtual base, then that CT, that is transient capacitor, what will be the name for that CT then? That CT will become a capacitor present between virtual base to collector. And this is a capacitor, look at this, capacitor present between virtual base to emitter. Look at this, this is what my CB dash C and CB dash E. So how many capacitors? Let me make a list. One capacitor is CB dash C, second capacitor is CB dash E. Now CB dash E is referred as diffusion capacitance, CB dash C is referred as transient capacitance. Is it? So 4 resistors and 2 capacitors are present inside the transistor, and those are responsible to decrease the gain at higher frequencies. The thing is clear? Is it? Now come towards that base spreading resistor. Is it? I hope you understand that RB dash C means a resistance, internal resistor present between virtual base to the collector. RB dash E, that is internal resistance present between virtual base towards the emitter terminal. And look at this, this is base spreading resistor. that is between virtual base to the actual base, and this is internal resistance present between collector and emitter. Is it? This is diffusion capacitance and this is transition capacitance, like these 4 resistors and 2 capacitors. Is it? Now let us discuss something about this RB dash B, that is base spreading resistor. Base spreading resistor. What is that? RB dash B. Right. You assume a condition where the transistor is in its actual operation of active region. Now look at this. I assume that there is an emitter. Look at this. This is emitter. This is a base. This is now for me it is a base, and this is collector. This junction is reverse bias. This junction is forward bias because the transistor is in active region. So transistor is in active region, one junction is forward bias, another junction is reverse bias. So when this junction is reverse bias, its depletion width is high. Obviously the width of depletion region is high. Somewhere here I have a base terminal. Look at this. This is terminal of the base, this is terminal of the collector, and this is terminal at the emitter. Now what happens if you increase reverse bias on this junction? If you increase reverse bias on this junction, then what happens? Then this width increases. This width will become now that much. Look at this. What I am doing, I am just increasing the reverse bias. If I increase reverse bias, the width increases. Width of depletion region. You further increase the reverse bias, then what will happen? Further the width increases. Now it becomes that much. Look at this. It becomes that much. You further increase reverse bias, then the depletion region width increases, and at a particular condition, at a particular voltage, at a particular situation, this base terminal, look at this, let me change the pen, this base terminal comes in the depletion region area. Is it? That base terminal, actually the lead that I am taking from the base, that lead comes under the depletion region. So now this is not actual base. इसको हम actual base बोल सकते हैं? No, it is not a part of base. What is actual base? Let me change the pen. Actual base is this. Look at this. This is what my actual base. This is actual base region. And the base terminal, this is not in the actual base region. And hence, there is a resistance present between the actual base and the base terminal. That resistor is called base spreading resistor, that is RB-B. This is what I have shown here, that is RB-B. Look at this. This is what. Now got the reference? RB-B base spreading क्या होता है actually? Actually, it's not a base region spreading. It's a spreading of junction or spreading of depletion region in the base region. So that's why it is referred as base spreading resistance. Is it? So this is all about internal capacitors and internal resistors of a transistor. Is it? So now those already we have marked with some resistors and capacitors in the transistor. Let us draw it in equivalent diagram. Let us draw it in equivalent diagram. How to draw? To draw the equivalent diagram of all those internal components, let me mark a base terminal. Look at this. Somewhere here it is. Okay, let me change the pen. Okay, this is a base terminal, or what I can say, virtual base. Okay, virtual base we marked with a small letter B. Okay, this is what my small letter B, virtual base. Okay, this is actual base, capital B. Then in between virtual base to actual base, there is a small resistor. What is that? Base spreading resistor. Just now we have seen R B dash B. Is it? Then let me draw a common emitter line. Look at this. This is what my common emitter line. So this line is what my emitter. Now from this virtual base to the emitter, I have one resistor. What is the name? It is R B dash E. See, two resistors I have marked out of four resistors. Two resistors I have marked. One is from virtual base to base, from virtual base to emitter. Now, somewhere here I have collector. Look at this. This is what my collector terminal. Let me draw the collector line. So this is what my collector. It's the collector line get tilted. Let me draw straight. I will try to draw the straight line. Okay, this is collector line. Now from virtual base to collector, do we have one resistor from virtual base to collector? Yes, we have one resistor in between virtual base to collector. Look at this. The resistor's name is R B dash C. Yes, 1, 2, 3. Three resistors I have shown. Is that? The fourth resistor is present between this collector and the emitter. That is R C E. Now check 1, 2, 3, 4. Four resistors we have marked. We have marked with four resistors. Look at this. 1, 2, 3. B dash C, B dash E, C E, and B dash B. B dash B, B dash E, B dash C, and R C E. Four resistors I have marked. Is it? Now it's time to draw capacitors. Now one capacitor is present between virtual base to collector. Let me draw it. What's the name? C B dash C. Another capacitor is present between virtual base to the emitter, that is C B dash E. Just check. 4 resistors, 2 capacitors I have marked. This is what my transistor. Is it? See, I'm not showing any biasing resistors. This is just a internal circuitry of the transistor. Is it? Look at this. This is a transistor only. Now for this transistor, what you will connect? You will connect R1, you will connect R2, then here somewhere your RC will be there, then RL will be there. Everything will be there. But what is this? This part is just a transistor. I'm showing internal structure of a transistor. Is it? So eventually what will be there at the output? Obviously there will be one small resistor RL. It's not small as such, but load resistor. It is optional. I am showing it with the dotted line. Is that? So those are the internal components, distributed components of a transistor that I have shown. Is that? Now, see, I didn't show any current, maybe input current or output current. I'm not showing any input and output current. But let me tell you that one voltage is there in this part. Look at this. What is that voltage? That is voltage present between a virtual base to the emitter, VB dash E. Now what is that VB dash E? VB dash E is the input voltage. Obviously that base is there at the input side. We are applying input signal to the base. So VB dash E is input voltage. Input voltage. I'm showing input voltage. As if I change input voltage, output voltage will change. That is the basic amplification. Now I'm showing input voltage. Somewhere I need to show output current also. Why? Because this input voltage and output current. Look at this. Input voltage and output, those are dependent quantities. One dependent quantity I am showing, that VB dash E. Another dependent quantity, that is output current, I need to show. But how to show output current? I just have a collector terminal. So do I need to show collector current as I shown in hybrid model? In hybrid model, what is that collector current? Collector current IC, I have shown HFE IB. So do I need to have the same thing here? No. Here what I will do is I will consider a transconductance. This term is purely new for me now. Transconductance, GM. What is that GM? It is transconductance. I'll write it here. Transconductance. What is the definition of transconductance? Transconductance is basically a ratio of output current to the input voltage. What is output current? If it is common emitter amplifier, output current is IC. What is input voltage? Input voltage, obviously it is VB dash E. Think about above circuit. VB dash E is the input voltage. Just now we have said. So IC divided by VBE is the transconductance. Is that? So we can consider the ratio of GM, that is IC divided by VE, when CE is constant. Now, output voltage has to be constant. Then only I can consider output current to the input voltage ratio. Yes, it is possible only when output current is constant. So this GM I need to consider here. What is my intention? I want to show output current. So from that equation, what is IC then? IC will be GM multiplied by VB dash E. This is what my output current. Look at this. That is what output current, and I will show that output current in the above diagram. So let me modify the diagram. Let me draw a current source here somewhere. Look at this. This I have to add. Now what is the value? The value will be GM multiplied by V dash E. That's what GM multiplied by V dash E, GM V B dash E. So this is what GM V B dash E I have inserted. Is it? Output current I am showing with reference of transconductance multiplied by input voltage. Is it? So this diagram, is it? This model, let me copy that model. Let me check whether it is possible. Yes, it is possible. This model that I have drawn here, this is called pipe model of a transistor. Let me paste it and let me rub the unwanted part. Okay, let me rub that unwanted part, and now let me tell you that this is called what it is called. Let me change the pen and let me write, this is pi module of a transistor. This is pi module of a transistor. Pi module is, or when pi module come in picture, at higher frequencies. So that's why if I want to analyze transistor amplifier at higher frequencies, I have to use pi module, because at higher frequencies internal capacitor and internal resistors of the transistor come in picture. They become active only at the higher frequencies. So that's why as they become active at higher frequencies, they create a higher frequency effect on the frequency response. And if I want to observe them, I have to create a new module. That new module is nothing but your pi module of a transistor. So henceforth we are going to analyze the transistor at higher frequencies using this pi module. So what is there in pi module? 4 internal resistance, 2 internal capacitors, and 1 output current that I have shown. Is it? This load resistor is purely optional. If you want to keep it, otherwise you can remove it completely. Is it? So basically what is that? It is pi module of a transistor. That was the intention for this lecture, to understand pi module. Is it? Now next lecture I will use that pi module to calculate the voltage gain. I will use that pi module to calculate current gain at higher frequencies. Is it? And I will put some conditions and criterias. What will be the gain when load resistor is there? What will be gain when low resistor will not be there? Those effect I need to observe. That is effect of frequency, effect of higher frequency instead on gain of an amplifier. Is it? So I hope this pi module part is clear now. So in next lecture we will apply this pi model. We'll use that pi model to analyze the transistor at higher frequencies. Okay. So if you want to, you can. I hope you have copied all those things. I'll share those after we finish this chapter. We'll finish the analysis of higher frequencies. Was that? So we'll meet in next lecture. Till then, thanks a lot.